All right, guys, so as I mentioned in the previous unit where we were talking about radicals and inverses, one of our motivations for talking about inverses was so that we can look at them in the context of what are called exponential and logarithmic functions. In fact, at the very end, we even looked at some examples of exponential and logarithmic functions. That's going to be what this unit is all about, and we're going to look at them separately, at least in these first two sections, and then the rest of this unit, we'll put them together and kind of compare them side by side throughout each section. So this section is going to be all about all about exponential functions. And in order to talk about exponential functions, we're first going to compare them to linear and quadratic functions. Those are two functions that we've already seen before this year and really are kind of the primary two types that we've looked at up until this point. Let's start by just writing out what each of these functions looks like. So for a linear function, typically we think about that in terms of its slope-intercept form, which usually we would write mx plus b. I'm just going to write ax plus b instead. Whereas for a quadratic function in standard form, that would be that y is equal to ax squared plus bx plus c. Finally, for an exponential function, we would write that that is y is equal to a multiplied by b to the power of x. And so what kind of separates the equations from one another? In a linear function, your degree is 1. You've got x to the first power. Quadratic functions, you've got x to the power of 2, so you've got x being squared. In an exponential function, the variable is actually the exponent, so you've got some other number to the power of that variable x. So when you're looking at an equation, that's how you can tell whether it's linear, quadratic, or exponential, is where is the variable and what is the exponent. Now, when looking at it in terms of a table or maybe a set of points, you have to look for what is the pattern between the y values. For a linear function, you're going to have what's called a constant common difference. And that's going to be a first common difference, so a common first difference. For a quadratic, you would actually have a common second difference, meaning you'd have to go through the y values a second time before you would be able to notice a pattern. And an exponential function, slightly different. That's going to be what's called a common ratio. And so we're going to look at some examples of both looking at equations and looking at tables and deciding what type of function are we looking at. Let's start with the equations. So our first equation, we've got f of x is equal to 2x minus 10 over 5. Now we can rewrite the equation if we'd like to, but remember all we really need to look at is what is the variable and what is the exponent. In this case, our variable is x, our exponent is 1. That would be what tells us that this is a linear function. Next, for number 2, h of x is equal to 5 to the power of x plus 7. So where is our variable and what is our exponent? In this case, our variable is the exponent. That's what's going to tell us that this is an exponential function. Finally, for number 3, we've got 1/2 x squared minus 15x plus 3/4. So where is our variable and what is our exponent? In this case, our variable is x, our exponent is 2. That's going to be what tells us that this is a quadratic function. Now let's look at how to determine what type of equation it is based on the table. So looking at this first example, if we look at our y values, and we're looking for patterns. To get from 6 to 10, probably the easiest thing to do would be to add by 4. From 10 to 14, we add by 4. And 14 to 18, we also add by 4. Notice that that is a common difference on the very first time we went through. That's going to be what tells you that this is a linear function. For the next table, we've got our values, and right away you can probably see that we're not adding, because for 1 to 3 we add by 2, from 3 to 9 we add by 6, 9 to 27 we add by 18, so that's not going to work. But it might be quadratic, and to be quadratic you just check it a second time, so from 2 to 6 go up by 4, 6 to 18 you go up by 12. That didn't work either. And so instead of looking at addition, let's check multiplication. From 1 to 3, we multiply by 3. 3 to 9 multiplied by 3, and 9 to 27 multiplied by 3. That is an example of a common ratio because you are multiplying. That's going to make this an exponential function. Finally, in our last table, let's always check addition first, and then you can check multiplication. In fact, if you tried to start with multiplication, you're going to find it pretty difficult to get from -2 to 7. I mean, I suppose you could multiply by -7/2, but again, I don't think that we can do that, and I don't think that you would even try to do that. Let's try addition first. So from -2 to 7, we go up by 9. 7 to 34, we go up by 27. And 34 to 79, we go up by 45. So no common difference, at least the first time around. Let's try the second time. From 9 to 27, we go up by 18. From 27 to 45, also up by 18. So now we have a second common difference, meaning it took us the second try before we found it. That's going to be an example then of a quadratic function. So now that we can tell the difference between linear, exponential, and quadratic, let's transition our thinking to just focused on exponential functions. As we mentioned, an exponential function looks like this. F of x equals a multiplied by b to the power of x, where a represents the initial or the starting value. So how much do you start with? And b represents the base, also sometimes called the multiplier. It is how quickly your function is increasing or sometimes decreasing. So just to do a little bit of practice with writing exponential functions, let's go ahead and write a couple functions for the given information. For number 1, it actually tells you a is 7, b is 1/2. So that should be pretty easy to write. We'll just put those directly into our equation. So a is 7, b is 1/2. We usually put a multiplication symbol in between the two, or sometimes we'll put parentheses around the multiplier, and then our variable is the exponent, so to the power of x. For number 2, it should be pretty straightforward as well, only difference being they don't tell you what a and b are, but when it says start value, that's your clue that 6 is going to be the a value, and for base, that's your clue that 3 is going to be the b value. So putting those into our function, we'll take 6 multiplied by 3. Again, either put the dot there or put it in parentheses, and then make sure to put your variable as the exponent as a power of x. All right, so real brief, let's talk about what the graphs look like. And for right now, just use a graphing calculator if you need to determine a graph of a exponential function. And in the later sections, we'll talk a little bit more about how to come up with those graphs by hand. But for right now, let's just focus on graphing calculator. So, exponential growth, we've got f of x equals 3 to the power of x. And in fact, we've got a graph of that. We've got a calculator screen kind of output there for you to look at, and definitely shows you that the graph is growing. Whereas exponential decay, notice that it is decreasing, but it doesn't continue to decrease forever. It does start to level out and does approach a certain value. In this case, for f of x equals 1/2 to the power of x, notice that it gets really, really close to the y value of 0. And remember, you're always reading the graph from left to right, so just keep that in mind as you're looking at these two side by side. Now, how could we possibly tell whether they were growth or decay just by looking at the equation if we didn't have the graph there to look at as well? Well, that all depends on what you're multiplying by. And if you think about it, there's one number that when you multiply by that number, it stays the same. And that's the number 1. If you multiply anything by the number of 1, that original number stays the same. So if that number is larger than 1, in other words, if our multiplier or our base is greater than 1, that means that our function is going to show growth. Whereas if that number we're multiplying by is less than 1, that's going to show what's called decay. So decay is just the opposite of growth. And so that makes it really easy to tell just looking at an equation whether or not the function is growing or decaying. So let's do some practice with that. On this first example, we've got f of x equals 12 multiplied by 2.5 to the power of x. And we want to decide whether this is growth or decay. Now, I suppose you could just grab a graphing calculator or go to Desmos and type it in and be able to tell that way. But even easier is to look at what your base is, which is the 2.5. And typically the base is what's inside the parentheses. It is always what is being taken to the power of x. In this case, 2.5 is definitely greater than 1. And since it's greater than 1, that's going to be our clue that this shows exponential growth. For the next example, our base is 1/2. 1/2 is clearly less than 1. That's going to be our clue that number 2 has a function which is exponential decay. Let's do one more example here. We've got 1/4 multiplied by 3 to the power of x. Here, that number inside the parentheses, which is 3, clearly is greater than 1, so this would be exponential growth. So, come up with an example of a function where it would be hard to determine whether it was exponential growth or decay. I'll leave that kind of up to you. One thing I might suggest is that fractions are sometimes hard to work with. If you had something like 5 multiplied by 7/6 to the power of x, 7/6, although it's a fraction, would be a fraction which is actually greater than 1. 7 divided by 6 would be, 1.16, and then the 6 starts repeating. And so just by looking at it, if you're not careful, you see that fraction and you might start to think decay. I'll leave it up to you to come up with some more examples of some functions where it might be kind of hard to tell if you weren't being careful whether the function was growth or decay. For the very last part of today's notes, we're going to talk about how to find a multiplier. Now the multiplier, remember, is the same as the b value. So when you see that word multiplier, that's what you want to be thinking of. And really, it's kind of a two-step process. Step number 1 is we're going to convert whatever rate we're given to a decimal. So oftentimes you're given a percentage, it's growing by 20%, it's decaying by 5%, and you want to convert that to a decimal first. So remember, to convert a percentage to a decimal, just divide by 100 or move the decimal place 2 places to the left. Either way will work. Step number 2 is then to determine your multiplier based on whether it was growth or decay. If it's growth, then your multiplier b is going to be 1 plus whatever your rate is. If it's decay, just take 1 minus your rate instead. So notice that it starts at 1 because really 1 is where it stays the same, right? And then if it's growth, you add to it. If it's decay, you subtract from it. But the 1 always comes first. Probably the biggest mistake I'll see people make is they'll try to take the rate plus 1, which usually isn't the worst. You can still get the right answer that way. The problem is when you try to take your rate minus 1. That's where you can definitely run into some problems. So make sure to always start with 1 and then either add or subtract the rate from it. Okay, so let's do some practice with that. Let's do some practice with finding the multipliers. We'll also go ahead and do some practice with writing an exponential function. We're going to assume that our starting value is 2 for each of the functions that we write. So for number 1, we're told that there is 3% growth. So step number 1 is we're going to go ahead and change our percentage to a decimal. So 3% divided by 100, or move the decimal over, depending on how you want to do that, is going to be 0.03. So when we want to find our multiplier, we're going to take 1, and since it's growth, we'll take 1 plus our rate. So 1 plus 0.03, which is 1.03. So then to write our function, remember that we said that the initial value, or the starting value, is always going to be 2. So f of x is going to be equal to 2, multiplied by 1.03, which I'll go ahead and just write in parentheses, to the power of x. All right, let's look to see what we would do if it was decay instead. So number 2, let's say we had 5% decay. Well, first of all, 5% as a decimal is going to be 0.05. And so if we want to find our base, since it's this time decay, that'll indicate 1 minus, whereas on number 1, growth told us to take 1 plus our rate. So 1 minus our rate is 1 minus 0.05, and that's going to be 0.95. So there's going to be our multiplier for number 2. Putting that into our function, f of x is equal to, remember the initial value is going to stay the same. We'll go ahead and put our multiplier inside parentheses, and then make sure to include your variable as the exponent, and here would be your exponential function. let's do just one more example of this, and then we'll talk about some exceptions to this rule, which don't happen often, but are things that you need to be aware of. Now, in number 3, we're asked to find the multiplier for 0.75% decay. Keep in mind that even though it says 0.75%, that is not written as a decimal yet. It does have a decimal in it, but it's written as a percent. So we do still need to move our decimal 2 places to the left, or we still need to divide by 100. That means that the decimal we're going to use is actually 0.0075. And then decay tells us that we're going to take 1 minus that rate in order to find our multiplier. So 1 minus 0.0075, and then make sure that you're careful with your decimals here. That's going to be 0.9925. So then putting that into an exponential function, again, we'll keep the initial value the same for these problems. But let's go ahead and write up what our new base is. So 0.9925. I'm going to put that all inside of parentheses to the power of x, and here's our exponential function. Now, there are some exceptions to finding the multiplier, and that's when they don't give it to you as a percentage or as a decimal, but rather they just tell you what's happening a little bit more directly. So an example of that would be where you're doubling it, and really what that means is that you're multiplying it by 2 every time. That means that your multiplier b is just going to be the number 2. So it doesn't necessarily follow that rule of changing it to a percentage. It just means that you have to kind of use some common sense to know that doubling means you're going to be multiplying by 2. In a similar way, if you have something, if something is being halved, then that means that your base is going to be 1/2. So you're multiplying by 1/2 each time, so it's getting smaller. The last thing you might see is where it might say something like it's being increased by a factor of fill in the blank, so maybe it's being increased by a factor of 3, in which case that becomes your base. All right, so that is it for exponential functions, guys. In the next section, we will switch gears and focus on logarithmic functions and kind of see how those are similar, but a little bit different from exponential functions. Until then, have a good rest of your day.